Okay, so the day we have all been looking forward to when we conclude the course. Okay, I thought you were looking forward to it because I'm going to do black holes. I'm looking forward to it because the course will end. Anyway, so today finally we will go back to our good friend the Schwarzschild metric, and we'll ask what does it actually mean if we go sufficiently close to the origin. And so to remind you, the metric is like this. This d omega 2 squared is shorthand. I've probably used it before for d theta squared plus sine squared theta d phi squared, the metric of the sphere. And Rs is just a free parameter when we solve the equation, but when we identify it physically with the mass of the object whose gravitational field this is, then we get this relation. Okay. Now, so far we have worked entirely with objects that are much bigger so they have a matter radius which is greater than this, and in fact in most cases it's much greater. We have seen, for example, that the sun has a Schwarzschild radius of only few thousand kilometers, while it's much larger than that. But there are objects for which these two things get very close, and for example a neutron star. So neutron stars are formed when there's a shell of matter, like a star, which is a spherical object that's burning. When it runs out of fuel, then so while it's burning, so burning means nuclear reactions are taking place, and these reactions create an outward pressure which balances the inward gravitational pressure. Okay, obviously there has to be some balance so that the star is stable and continues to burn, but at some point all the nuclear reactions which convert the elements in it to higher and higher atomic number, I believe they reach iron or something, and then after that you can't really burn it anymore in a nuclear reaction and gain energy. So then it just gets cold, and now it will collapse. And when it collapses, okay, I'm not that familiar with all the details, but my understanding is that it collapses, creating a huge kind of shock wave inwards, and then there's an outer part so this inward thing which is being squeezed blows up at some point, and a large part of the outer matter gets thrown off, and that's a supernova. It's called some collapsed supernova, I think. And then whatever is left is extremely dense and extremely small. And these objects in astronomy go by the name of compact objects. And there's an example where this neutron star, which has a name, it's called PSR J0740 plus 6620, and its mass is about twice the mass of the sun, but its size is actually just 12.5 kilometers. Okay, and its Schwarzschild radius is 6 kilometers. Now I'm a little confused because I thought I had a figure for Schwarzschild radius of the sun. Was that in meters or kilometers? How much was the Schwarzschild radius of the sun? Anyone remembers? 2000 kilometers.
2000 meters.
That's what I'm wondering. I think it must have been meters, because this is bigger. I mean, this is bigger than that of the sun by roughly factor of 2, and so is the mass. It scales as the mass. Everything else in this formula is just a constant. Anyway, so the point is that there has obviously been a physical process where matter has been compressed enough that its matter radius is only twice its Schwarzschild radius. So if there's such a tiny factor of 2, it's very reasonable to think that some process might compress some other matter more, so that this actually number comes down below this. Okay, and if that happens, then this solution is valid even for r less than rs, as long as r remains above the matter radius. And this is an object that now we call a black hole, and I'll try to justify that. So let me say, if Rm is less than Rs, then we can use this for Rm less than R less than Rs, as well as, of course, the usual. Nothing surprising will happen as long as R is greater than Rs, okay? Because you can see that this solution for all R greater than Rs has roughly the same characteristics. It just may define details, but it's the same solution anywhere outside Rs, okay? But if Rm is less, that means that the structure of this thing is that the real sphere, which is the matter, is less than the imaginary sphere Rs defined just by this formula. It's not a real surface, it's just an imaginary thing in space-time. So far, we'll see later that it actually has some more reality than that. But if this happens, then obviously we can work with the solution here as well as here, because there's vacuum in both places. That's all I'm saying. Okay. So now we want to understand what such an object would be like if it exists. And we are going to recycle a few formulae that we already derived, which can be very conveniently reused. So we recycle both light and matter trajectories in this metric, but with one change. We'll choose our light and matter trajectories to have zero angular momentum. Okay. Earlier, if you remember, we started with massive object doing elliptical orbits. Obviously, if it's doing any orbits, it has angular momentum. Okay. Then we went on to study light, which was grazing incidents around past the surface of a star, and that obviously has angular momentum also, because it's not heading straight for the origin. Here we are going to consider radial trajectories, and for radial, L is 0, and L being 0 actually simplifies the equations we have already written down. You just look at them and just put L equals 0, you will get new formulae, and you can ask all kinds of things about what does light do when it goes towards the origin of the Schwarzschild metric. We just aim it like that, impact parameter is 0. And we can also ask what happens if I have an observer who just starts very far away, let's say almost at infinity in a sense, and then just lets themselves fall. Well, they are subject to a rate, they start at rest, so they have no angular momentum, and then they let the gravity of this object pull them, and of course they'll also fall along the same straight line. Okay? The fact that it's a straight line is not in dispute. But we might ask questions like how fast do you fall, or what happens to light, or for example, what is the redshift of light between somewhere there and somewhere there. These are all questions we are going to ask. And some answers we get will be very reasonable, and some answers we get will be very shocking. So we'll try to do the calculations and figure out what we get. Okay. So the first thing we can say is that if you look at the metric, I wish I had not rubbed it out, just rewrite it here. Those terms will not matter. Now, earlier we had set theta equals 0, now we are also setting phi equals 0. So no angular dependence of the motion at all. And so for light, we just have to set this whole quantity to 0 because ds is 0 for light, and solve it for dr by dt, or dt by dr, however we like. And the way I'll write it is dct by dr is equal to plus or minus 1 over 1 minus rs over r. So this is what light will do. Okay. And it's clear that as I go to infinity, this factor becomes 1, and then this is just dct by dr or dr by dct is 1, which is the same as light traveling at the speed of light, which it will do at infinity. Anywhere else, it will travel at a speed which will vary depending on my coordinate system, so it's much more complicated. But at infinity, everything should be back to normal because special relativity applies. Okay, good. Okay, now let's and let's note that there are two signs y. The plus sign means that as time increases, r increases. So it's an outgoing ray. And the minus sign means it's an ingoing ray. And now we'll talk of experiments where we send light from infinity into the Schwarzschild solution, but we may also ask for situations where somebody over here sends a flash of light out towards infinity. And there's no symmetry between these, because in one case it's coming into a gravitational field, in the other it's going out of a gravitational field. They're quite different physics. So therefore we need to keep track of the sign carefully. So here you only get the squared equation, and when you take the square root, the sign is there, and the sign has a very important physical meaning. Good. Okay, now let's ask the question, what happens if r is allowed to approach rs? So at r equals rs, metric diverges. Actually, it goes bad in two ways. dt squared drops out, and dt is not there in any form in any of the other terms. So dt itself vanishes from the metric. Okay, so it's a metric of apparently of one lower dimensional space-time with no time. What sense does that make? On the other hand, dr squared, the coefficient blows up. That's also very bad. Okay, and you can see from this that the relation between time evolution and motion in radial direction starts to scale. And actually there's a way that we can depict this, which is the following. We have a thing called the light cone, and if this is my object, with this being rs, then here at infinity I have a light cone which looks like this. I'll just draw the forward light cone. There's also a backward light cone. Okay, and as you know, these lines are at 45. This is CT against X, against R, sorry, and these are 45 degrees. And all causal signals can only go in that direction, towards the future. Anything I do can propagate towards the future only like that. If it has to go out, then it will be traveling faster than light. So at infinity, this is what it can do. Now don't mix up, this t-axis is in the light cone. It's not part of this diagram. This is just a picture of a star, okay, at a fixed time. I'm just drawing the way the light cone looks as I come closer, and this formula tells me that when I'm here, the angle of the light cone is greater than 45 degrees. It has increased. So there was the light cone. As I come closer, it has kind of become like that. Okay? There are less, and if you like, there's less volume in space-time to go into the future. There are more of space-like and less of time-like region. The Schwarzschild solution is distorting space-time, so you're not surprised that light cones fluctuate or vary in their shape in different places in some coordinate system. remember that it's a coordinate system effect. We can hopefully change to other coordinates and maybe the light cones will do something else. But in these coordinates, this is what they do, and that comes from this. Okay, because that slope is dt by dr, and you see it's getting larger as r goes to rs. And finally, when we reach exactly here, the light cone has actually vanished. Is just collapsed. Okay? So that is the problem with this metric, that at r equals rs, the light cone has collapsed. So obviously you can't do any physics if there is no future direction. All of physics relies on one being able to propagate signals into the future, but the future is sort of gone away. And now we need to think. So that's one effect, that's one observation. The second observation is that in this metric, for r less than rs, something very weird happens. When r is less than rs, this factor is greater than 1. So this bracket is negative, this bracket is negative, and therefore the coefficient of dt squared has a plus sign and the coefficient of dr squared has a minus sign. Okay, so it means that r is a time coordinate and t is a space coordinate. And this is absolutely shocking. Time and space have reversed their role as I cross r equals rs. It just shows from this metric. Now you could argue that this is not very convincing because I can't actually use this metric to describe any physical process where I start outside and go inside, because on the way I'll reach r equals rs, and there definitely this metric doesn't work. It seems to work outside, seems to work inside with a different interpretation, but it certainly doesn't work at that point, r equals rs. Okay, are all these points clear? In particular, this r is a time coordinate. Is it clear why? Yes.
So you are saying it is a time coordinate because the coefficient is similar.
Yeah, that's the only way to define what's a time coordinate, right? You know another way, just because I call it t is not a good reason. Okay, I think I'm tempted, if I give you in the exam the metric this, what is this the metric of? And what are the t's? And what is x? You can call it anything. You might know there's a famous story about an admission interview where the interviewer wrote this equation and asked the student what is it, and the student said this is Ohm's law, where this is the voltage, this is the current, and this is the resistance. Okay? And it's very sad that there are a lot of interviewers who get angry about this. I would simply admit the student right away without any more questions. Okay? If you don't have that level of abstraction, if you think that F always means force, then you are just parroting something. You're not actually learning anything. The relation in this equation as well as in Ohm's law is that some physical quantity is product of two other physical quantities, and we can call them anything we like. So, not to make fun of you in any way, it's a good question, because actually it causes endless confusion when people see it for the first time, and you're very right to bring it up. Okay? The point is that what causes the ds squared to decrease when it grows is the time. What causes it to increase when it grows is the space. That's why plus sign means the space and minus means the time, and that's how it looks unless this factor is negative, and then the signs do switch. Okay. So now the question how to deal with r equals rs.
Excuse me, sir.
Yes.
So like R is phase, so like you can go forward and backward.
R is time. Time only goes forward.
No, but now you
Yeah.
change it to.
It's actually minus r, which is, r is time, means it's a time coordinate. We'll come to it. Patient. We are going to discuss all those things. And if I don't have time, you'll have to read about them. It will in practice mean that once I'm inside, r decreasing will be the future. Okay. Okay, so what do we do about r equals rs? Now, as you know, and you have done these examples from the very beginning of the course, there are two ways you can think about a point where the metric is behaving badly. One is that something is wrong with space-time, and the other is that something is just wrong with our coordinates. So which one is it? And so fault of the space-time or fault of coordinates. And there are no hard and fast rules to figure out which one it is. Yes.
I think that in this situation you can answer it this way, like when a body starts to collapse, some part of it on its surface does cross the Schwarzschild radius. So that means that it should be a coordinate problem and not anything wrong with space-time. Because physically things are moving inside the Schwarzschild radius, right? Like when it collapses.
Well, as we'll see, physically it's not very clear what is happening inside the Schwarzschild radius. Because we'll soon see that no signal can come out from it. So that's one thing. This problem confused Einstein for many years and confused everybody for many years. Which one is the case? The point is there are two options. One is, yes, what you want to say is that something is collapsing, and nature is not evil, so if something is collapsing, the space-time must be reasonable because it's actually happening. The other more doomsday kind of view is, well, by collapsing, this star has created a disaster and space-time has kind of gone to hell and there's no proper space-time anymore. And now, because that is the case, if we ever come to that place which is so dangerous, we'll all be kind of wiped out and destroyed. I mean, so it's a question whether space-time remains well behaved under time evolution or not. Now, there are differential equations which become ill-behaved under time, where the solution becomes ill-behaved under time evolution, so it's not impossible. You can, even I think in the context of fluid dynamics and so on, you can have ill-behaved features. So it's a very subtle question, sure. And there's no simple answer and there's no algorithm to answer it, but we should always resort to curvature. How is the curvature behaving? If the curvature is behaving bad at that point, like diverging, then the space-time has gone bad. There's nothing we can do about it because curvature, especially the curvature scalar or any scalar made of it, is completely invariant under change of coordinates. So if curvature is going to diverge, then no change of coordinates can solve that. That's the end. However, r mu nu, which is the Ricci tensor, is equal to 0 because this is a vacuum solution and left side of Einstein equation is r mu nu minus half g mu nu r, and r is nothing but contraction of metric with r mu nu, so both are 0. So only r mu nu lambda rho is non-zero. Some of the components of this will be not zero. Not all components, but some components will be non-zero. So we could look at this, which is a little bit tedious calculation starting from that, and we wrote down probably some formulae for it. But the problem is this is coordinate dependent because it has 4 indices, so under every coordinate change it will change. But there is a tensor which we can form, there is a scalar we can form from it by contracting this. This is the Kretschmann scalar, we discussed it. And the advantage of this is the first scalar that we can form from the Riemann tensor in a Ricci flat background, a background which solves the vacuum Einstein equations, is the simplest scalar you can form, which is not trivially 0. Okay, it's not the only one. You could have 10 R's with all their indices and then contract them, one here, one there, one here, one there, in millions of ways. You could have many such scalars. But this is the simplest one. More complicated ones will have at least 3 R's. And this one we can calculate, and I've already told you the answer. So it turns out to be 12 Rs squared upon R to the 6. You can also write it in terms of GM. But now you see this thing is very innocent. It knows nothing goes bad about it at r equals rs. It's perfectly smooth all the way to r equals 0, where it diverges. So from this we can actually draw two conclusions. R equals 0, space-time is singular. I want to emphasize that this is a proof. Because this is singular, space-time is singular. So there is a place where the collapsing matter has actually destroyed space-time. And let's contrast that with, say, Earth, which is not collapsed matter. If hypothetically we were to dig to the center of the Earth, we would certainly not expect to blow up like this. We wouldn't expect anything to happen actually, except that there'd be zero gravity over there. Earth's gravity, it would be decreasing till we reach there, and there it would be zero. But certainly the center of the Earth is not some awful place in space-time or in space. But in this solution, if we allow ourselves to go to r equals 0, then it's singular. Now you could again say that we are not allowed to go to r equals 0 in this solution because because there's still some matter, except the matter went inside. But that it's more confusing than that. We can only say that the metric, the space-time described by that metric, if we take it seriously everywhere, it's singular at r equals 0. This is a fact. Now the other side, at r equals rs, we can only say that space-time may be smooth. This being smooth is no guarantee that space-time is smooth. It simply allows the space-time to be smooth. To find out that it is smooth, I have to do more. What should I do to prove that a space-time is smooth at some point when the coordinates are showing singularity? You know the answer to this. Change the coordinates, exactly. So I should, if I can find a change of coordinates in which it's smooth, if I can find one set of coordinates in which it's smooth, I'm done. It's smooth. Over. But the problem is, how do I know if I can't find it, is it because I'm not smart enough or they don't exist? Very hard questions. So these are very tough things. Yes?
Isn't this a proof that it's not diverging?
No. It doesn't prove that so it proves that this combination is not diverging. That's all. It doesn't, first of all, this itself I don't think proves that other scalars will not diverge. And even if all scalars don't diverge, all curvature scalars, scalars made from the Riemann curvature don't diverge, apparently there are still weird space-times. So this is what mathematicians always like to do, counter example. And so at least I was told by my good friend and these days only friend, ChatGPT, that there are space-times where all the curvature invariants are smooth, but the space-time is still singular at that point. When I said these days it's my only friend, it's because I have worked very hard to prepare these lectures, not for any other reason. Okay. So the only hope is to find a change of coordinates. But before we do that, let's ask a little bit more about the physics of these radial trajectories, and we'll quickly find out something very interesting. So if you remember, for matter, first we'll do it separately for matter and for light, because we want to consider both possibilities. Matter will be anything with a mass, small m, and that will be an observer. An observer always is made of matter. Light, on the other hand, is the massless case, so we have to take the massless equations that we developed very recently and then just for null trajectories, and then just specialize to radial case. So for massive case, the equation is half m dr by d tau squared. Then there's a potential I have to add, and that potential contains this term. Now there was an angular momentum barrier term, L squared by 2r squared, but now I'm working at L equals 0, so that's gone. There was a GR correction which was also proportional to L squared, that's also gone. Everybody is gone. And what is the right side? it is the quantity which we wrote as E squared by 2mc squared minus mc, half mc squared. This all we have done and it's all in the notes. Now let me assume that I am dealing with a concretely with an observer who's traveling on this, and I'll call that observer O in, because this observer started at infinity at rest. So just a person who starts very far away from a planet and then just lets go and falls. We want to know what is that person's trajectory, and it's very simple from this equation, because E is conserved. Okay, we've done that because of the time-like killing vector of Schwarzschild. And what is E at infinity of this observer at rest? 0. mc squared, thank you. Okay, with E equals mc squared, what is this quantity on the right side? 0. Very good. Excellent. So this observer O in starts like this. So with E equals mc squared. And for this person, I will write tau in, because I want to know something about the proper time, how it behaves for that observer relative to some other observer who might be remaining at infinity. You can imagine two friends at infinity, one agrees to fall in and other waits at infinity. Okay. To really wait at a fixed radius from a gravitating body, you need to accelerate yourself. You're not following a geodesic, but we'll just assume that person has a rocket ship which is just keeping them stable at some distance far away from the planet. Okay, good. So now we can solve this equation, and we get that dr by d tau in is equal to, we take the square root, we put the factors on the half m factor on the other side, we set that thing to 0. So this thing goes to 0. And we get this is equal to minus c root rs by r. You agree? Here there's a half. If I take it here, this will be 2 gm. Okay, there's a tau, there's a c factor that I lost somewhere. Where did I lose it? Oh. Yeah, so this is 1 by c is equal to this. Is that clear? Maybe I should do this here, it will be clear. So this equation becomes dr by d tau in squared is equal to gm by r times 2. Okay? So now I divide both sides by c squared. Now I take the square root. So now the right side is equal to rs upon r. Okay? So now I take the square root and I get 1 by c dr by d tau in. And again I have two signs, but what sign do I want to take? Ingoing, so minus. So this is the answer, and there's a square root. Because this is this, so here there's a square root and then I take the minus. So this is the result for this observer. Okay. For the same observer, I can also use the killing vector equation which I wrote earlier to find the rate of change of the coordinate time. This t is the Schwarzschild time, which is a fixed t for all everywhere outside, as long as we are outside. This t is one of the coordinates. So what is the rate of change of t with respect to tau? That you can easily find is 1 over 1 minus rs by r. So we have dr by d tau in and we have dt by d tau. Good. Now with this information we can already see something interesting. Look at this equation. the observer is falling in, and in her own proper time observing her velocity to be this factor times c. The minus just says that it's inverse, okay? Now as r approaches rs, dr by d tau just becomes minus c times a factor which is approaching 1. So what can we say? The observer is approaching the speed of light. So the observer falling freely from infinity to rs, this is approaching speed of light over here, dr by d tau. Very good. So falling very fast. Okay. Now let's add the new observer. This observer is O in. And this is an observer who at any given instant can be at any r varying from infinity to rs, because we are going to trace her progress along this path. Okay. But we have another observer, O infinity, who, as I said, sticks to the place at infinity, stays in one place, says bye bye to this person, and then says, you please send me signals as you are falling at some intervals, and I will also send you signals. So our job is the following: each of them starts sending some light flashes at intervals of 1 unit in their coordinate, in their proper time, and we want to know how those light flashes look when they are received from by the other person. What is the spacing? Yes.
Tau is the proper time of the individual falling inside.
Tau in is the proper time of the infalling observer, and tau infinity is the proper time of the observer at infinity.
Then how is dr by d tau the speed of the observer, of the infalling observer?
As seen by that infalling observer.
And their own speed seen by the infalling observer would be 0, right? Because they are.
Yeah, no, it's not. That's not it. It's not their own. It's their distance to the center.
Right. Okay.
Changing as a function of time.
Right. Okay. And then dt is the over there.
Is the coordinate, Schwarzschild coordinate time. The coordinates in Schwarzschild are t, r, theta, phi, of which theta and phi are dead, so r and t are the coordinates. It's just an intermediate step. We are not going to.
Okay.
Well, maybe we will worry about dt in a moment. Let's see. So good. So now, as we said, O infinity emits signals spaced delta tau infinity, that amount, and O in emits signals spaced delta tau in. This is the same in the sense that these are two separate experiments. So in the first one, this person emits signals spaced delta tau infinity, let's say is just some fixed amount, and we want to know delta tau in for those signals. O in emits signals spaced delta in, the same units, and we want to know delta tau infinity. Is it clear what we know and what we want to know? The emitter has a fixed rate of emitting. We want to know what is the receiver receiving. In the first case, O infinity is the emitter. In the second case, O in is the emitter. We can't compare these two lines. They are two separate experiments completely. They may happen at the same time, but one is the light is falling in, the other the light is coming out. It's reasonable to think that the answers will be quite different because of the asymmetry of light going in and light coming out. Then in fact they are very different. Okay. So how do we calculate these? Let's start with the first one. So for this, recall that for light we had derived this equation for infalling light. And now let's try to integrate it. Okay. So we learn that Ct is equal to minus r star of r, which is a function which is nothing but the indefinite integral of this thing. Okay. And let's write it. It's very easy to calculate. You just evaluate this integral, which requires multiplying by r and doing few things, and you find that r star of r is a function given by r plus rs log mod r by rs minus 1. And I have a feeling I have typed something wrong. I think this was meant to be log rs over r minus 1. Because now, if I go to infinity, this term this term becomes log of 1, which is 0, and r star becomes r. That's compatible with this equation where this term drops out at infinity, and integrating this just gives me that Ct is equal to minus r. All right. So r star is a new variable which basically keeps pace with the time obtained by integrating it. Good. Okay. Now let's see what happens at infinity. Okay. Now there's one more thing. We rewrite this equation as V of r is equal to Ct plus r star of r and is equal to 0. Okay, just take this to the other side. So I call this V. So light follows this. Now the person now what we are going to do is this V is 0 throughout. Okay. So an interval in V at infinity and an interval in V at this person, we will equate those two. Okay. And that will tell us what is the relation between the proper time at infinity and the proper time at that person. So what is the interval delta V at infinity? Well, this is of course infinite. So this is just r at infinity, and that's held fixed. So we get C delta t, and this is the same as C delta tau of the person at infinity. What about delta V for the infalling observer? For that we need to use an equation, because for the infalling observer, this is not constant, this is varying. So this will also contribute to delta V. So the equation is dV by d tau in is equal to C dt by d tau in plus dr star by d tau in, but we'll write this by chain rule as this. And we know all the terms. We just few minutes ago calculated this. We got some square root form. We calculated this. And this we know because it's part of the change of, it's the integral. Dr star by dr is just this factor. So if we assemble everything, we get for these two factors C common, and then we get 1 over 1 minus rs over r here, and here we get minus because this is negative, square root of rs over r, and again 1 minus rs over r. If I add these two, I get 1 minus square root over 1 minus this, but I can rationalize that to get, or opposite of rationalize, to get this. So this is my answer. And it follows that delta V is equal to C over 1 plus square root of rs over r times delta tau in. So this is one equation. This is the other equation. So I don't have to say delta V infinity. It's just the same delta V. It's this. Okay. So I just equate these two delta V's, and I'll get a relation between delta tau and delta tau in. I want to solve it for delta tau in because delta V, delta tau infinity is the one, that's the person who's emitting. So that person's thing is fixed by a clock. I want to know what this person is receiving. And that's very easy. It's a, what is the time?
2:51.
Still have a few minutes, no? So we get delta tau in is equal, as a function of r, is equal to 1 plus root rs over r delta tau infinity. And that means that as this person, so first of all, if this person was still at infinity before they left, then their delta tau and the delta tau of their friend at infinity are the same, obviously. Now this person is coming closer and closer to rs, and this number therefore is actually increasing. As r decreases, this number becomes larger and larger. And so this interval is larger than that. That means the clock is ticking slow. So this person sees longer spacing. This one is fixed. This person sees the ticks are coming at longer intervals. And those intervals keep increasing until this person hits RS, where the interval becomes
Equal.
no, where equal. R equals RS. What is the real?
1 plus roots. 1 plus
1 plus root of 1.
yeah.
Root of 1 is 1. Yeah, 2. Good. We all have that. So 2. Yeah. R tends to 2. So there is some shift, but it's not terrible. The person who is reaching the R equals RS says, okay, this time is slowing down for me at by a factor of 2. That's as bad as it gets. Okay. In terms of redshift, you can evaluate the same thing by just flipping this, because the frequency will be inverse to the time interval. Okay. And so you will see that whatever light is sent from infinity, the color of that will have turned slightly redder by a factor of 2. Wavelength will double. That's not something terrible, but say if it was 3000, it will turn into 6000 angstroms. So it goes towards red. Okay, so redshift. However, if we ask the reverse question, the person inside sends the signal to the person at infinity, you might think that the formula is just inverted. This comes the other side. But because light is moving out, you cannot use V anymore. You have to use a different function U, which is not Ct plus R star, but Ct minus R star. So it changes the sign. And so you get a minus sign. This is an exercise for you. So reverse experiment says that the signal received at infinity is 1 over 1 minus root Rs over R, signal emitted by this person. This is the second experiment where this person is emitting. It's the same formula, but there's a minus. You have to work out why there's a minus, and as I said, it's because light is going out. Now, we see something totally bizarre. Again, this person sees a redshift. Both ways they see a redshift. This is also increasing as R decreases to Rs. But the weirdest part is that it increases to infinity. So, Rs, that means this person waiting at infinity for news of their friend is getting the news less and less and less often, and simply stops getting news altogether at some point. Okay. Another way of saying it is, they never observe their friend falling inside the horizon, though the friend does. She's moving at the speed of light. She actually goes blissfully right through. But the person at infinity feels that she has slowed down and is asymptotically approaching the horizon and getting slower and slower in her behavior. So it's a very different thing. And here you have infinite redshift in the limit. Very important fact. That means the light which this person is sending from near the object is coming out deeper and deeper red at infinity, and there's no limit. Okay. Now I have to be brief. You people have another class, or is there another class in this room? Exam. Now.
Physics lab.
Who has? You have.
Yeah.
At 3.
Yeah.
Okay. Oh. Okay. So let's condense the rest of it. Now, if you have studied this thing called Eddington-Finkelstein coordinates, which I've already done, you'll realize that this is exactly where we need to apply it. because what we do is we take this V of r, which is t plus r star of r, and we make it a coordinate. Right now it's a function of the coordinate t and r, but we eliminate t in favor of v, and we find that the metric, Schwarzschild metric, is minus 1 minus rs over r dv squared plus twice dv dr plus this hasn't changed. And you see the amazing fact that nothing goes wrong at r equals rs in these coordinates. We have got rid of time. What happens when r is equal to rs? This drops out, but dv doesn't disappear, it's there. Okay? And when r becomes less than rs, this changes sign. So v, asymptotically it's time-like. On the r equals rs, it's null, and inside it's a space-like coordinate. It actually flips what it's doing. R is always null. And this is very convenient because now you can follow light ray trajectories for r just as the along that coordinate. You just vary r, keeping everything else fixed, and that's your light ray. Okay, but this shows that the solution is everywhere smooth. And this is a proof that there is no singularity at r equals rs. Okay. The last thing we need to do, and it will only take a couple of minutes, is to ask what happens to outgoing rays once the person is inside. We've already seen that this person, as they approach the surface, r equals rs, their signals to infinity are getting slower and slower. What is the only possible continuation of this as the person goes inside r equals rs? Their signals never reach infinity. Okay, because they have got slower and slower to a point of being infinitely slow when r is equal to rs. So the only logical thing to expect is that when r goes below rs, signals never go out. But that's just expectation, and all that discussion was in Schwarzschild coordinates, where we are not supposed to talk about that because those coordinates are bad at the r equals rs surface. What we did up to now was only like a limiting behavior as r approaches rs from outside. We never actually went to it. Now we want to go to it, and we want to ask what happens to outgoing light at r greater than rs and r less than rs, and compare. For that, we just have to set this equal to 0 and find the equation for dv and dr. Now, one of the solutions is dv is 0. What is that solution? We've already seen it. What is dv equals 0? That's the original ingoing ray. We've just made v into a coordinate, but dv equals 0 is the ingoing ray. So there's another solution here which has to be the outgoing one, and that solution is dv by dr is equal to twice 1 minus rs over r. And now we see something very interesting. Very far away when r is infinite, dv by dr is a constant, so it's outgoing, right? V increases. V is like playing the role of the time. I told you it's time-like. V increases, r increases. You can also think of V as t plus r star. There also you'll see that as time increases, r increases. So when r is greater than rs, this is outgoing. But when r is less than rs, dv by dr is minus of a positive quantity, because now this becomes r is less than rs, this whole thing becomes negative. So dv by dr is negative. And therefore, here it becomes ingoing. And now we have the ultimate paradox, and I'll stop here actually. The ingoing ray is always ingoing. The outgoing ray turns ingoing when you're inside this r equals rs point. So this is the picture. Here is rs. Here is one ray which goes in at dv equals 0 and goes out at dv by dr equals 2 into 1 minus rs over r. Everything is good. Light can either go in or it can come out from this region. But here, dv equals 0. Let's remove this arrow. Continues like this. V just smooth. V is a coordinate, so it smoothly goes through. Yeah.
How long do you have?
Yeah, almost done. 1 minute. On the other hand, this one now points this way because the sign has changed. So the ingoing ray is ingoing, the outgoing ray is also ingoing. All rays are ingoing and there are no directions outgoing. No outgoing light rays once we are inside. And so we learn that a black hole is one which has no outgoing light rays. It's not something so strong that it captures light as is so often said. It is something which distorts space-time in such a way that inside its horizon or Schwarzschild radius, it turns all directions to point in. That's the bottom line. It just twists the directions of flow of time to be inwards. Yes. At r equals rs, what happens is that the light ray goes along the horizon. So this r equals rs, it's a sphere, okay, but it's actually it's a sphere translated along time, right? Because it's a space-time. If I fix r, there's still v theta and phi. So it's a three-dimensional space-time. That's actually a null hypersurface, and it turns out that these light rays are tangent as well as normal to that null hypersurface. So I explained that in my last lecture. Were you there? In a null hypersurface, tangent and normal are the same thing. You were there. You asked questions. Yeah. So So this is it. This is the point. So actually, what happens, if you like, is okay. And finally, let's draw a light cone. The light cone is like this here. It starts tipping till the light cone becomes tangent. Starts tipping like this. And here the light cone has fallen over so that all future directions are inside. No future directions are outside. The light cone has tipped over. And I'll stop there because they need the class. So thank you.